was like that. That's what I was
Oh, wait.
All right, guys. Okay, real quickly, I want to run through this very last part of part one and just kind of make sure that you understand what's going on with these and how you can use combination permutations as well. So here's an example. This is at the back end, right before part two. This is still part one. It says a bag contains 5 red, 9 blue, and 6 white marbles. 3 are selected at random. Find the probability that you get 3 red balls. So a lot of people starting out with probability, they fail to realize that the order in which you choose something can have an effect on the outcome. Okay, what I mean by that, and you're not going to see it here, but you're going to see it as I progress through these similar problems. So a lot of people go, oh, well, what's the probability of getting a red ball? And they go up there and they go, all right, first probability would be 5, because there's 5 of them out of a total of 20. And they say there's a 5 in 20 chance. And by the way, don't bother simplifying this stuff to 1/4. Just go with it. The simplifying part is not important to me. All right. Now, once I take that red ball, now the chance of getting a red ball diminishes, right? Because I no longer have 5 red balls. I have 4. And now I also no longer have 20 balls total, right? There are now 4 reds out of the 19. So the next choice for getting red would be 4 out of 19. All right, now once I pick that red ball, now I only have 3, and I have only a total of 18. So the final red right here would be a 3 out of 18. Now in this particular case, that is the probability of getting 3 red balls. But what I failed to even think about was the fact that could the red balls be taken in different orders? Bottom line is, it's not going to show up in this problem because red, red, red is the same as red, red, red. But if I had 2 reds and a blue, red, red, blue is different than blue, red, red, isn't it? So the order in which something could have happened could have affected this outcome. Now, if you remember, if I want to count how many ways I can rearrange letters, like the letters in the word Mississippi, if you remember that, when we had the letters in the word Mississippi, there were 11 letters, so there's 11 factorial ways I can do that. Kind of like there's 5, 4, 3. It's kind of like a factorial there, 5, 4, 3. But there are 11 factorial ways I can rearrange Mississippi. However, there are 4 I's, there are 4 S's, and 2 P's. So 4 I's, 4 S's, and 2 P's. Technically, there's 1 M as well. That's how many ways I can rearrange the letters in Mississippi. Now, my letters are R, R, and R. So there's 3 factorial ways I can rearrange 3 R's, just like there were 11 factorial ways I could rearrange those letters. But because they're all the same, 3 factorial over 3 factorial would have canceled and left me nothing but 1. So in this case, it's very easy to think, oh, I don't need that thing out front. But you do need it out front in terms of a good habit, because if the order is not specified, if I don't specify what order I have to take them, then I have to count all those different ways that it could happen, because that increases your probability. Right? I mean, think about it. If I said, what's the probability of getting a blue and then a red and then a red? If I said that and you first pick the red marble, do you have any chance of being successful? No, because I said a blue and then a red. You're already messed up. You already failed. This probability failed. So I don't have to count the other ways that might have looked like this or might have looked like this, even though I got the same kinds of marbles. But if I do say, hey, what's the probability of getting 2 reds and a blue? Well, 2 reds and a blue can be done 3 different ways. Are you with me? Or how about 2 reds and a white? Because that's what this problem is. 2 reds and a white can be done 3 different ways. And if I don't count them, I run the risk of making the mistake that I didn't make up here by forgetting that. See, this would have canceled. I didn't need it there because they were all the same. But here, look, if I were to say, all right, what's the probability of, if all I would have done is this, probability of getting a red, 5 and 20. Another red, 4 and 19. A white, 6 out of the remaining 18. If I don't put that in there, then all I'm doing is finding the probability of getting a red, and then a red, and then a white. And that probability there is not my answer in this case, because I have failed to add to that the other ways of getting probabilities, which are that way and that way. Now, all three of these are going to be the same. But rather than add the probability, the same probability to itself 3 times, I would rather just multiply by 3. And I can count these easily, right? Oh, the red could be, the white could be first, last, or in the middle. But when I can't count it easily, that's where this part out front comes into play. Because I can basically ask myself, how many different, think about it like words. How many words could you make from these 3 letters? Well, there's 3 factorial ways to arrange them, 6 ways, but switching the 2 R's doesn't change anything, does it? It still looks like RRW. So I divide it by 2 factorial for the 2 reds, just like I did for the 4 I's and 4 P's and 2, whatever, and then 1 factorial for the white. That counts the different orders. And again, I don't mind you if you can count them individually doing that, but it's going to be harder and harder. Like, what if I said, hey, I want you to pick 5 reds and 3 whites? Well, that's 8 different marbles, right? How many different ways could you do that? That would be really hard to calculate. But if there's 8 marbles and you go 8 factorial over 5 factorial, 3 factorial, the math's sitting there waiting for you. And we're not simplifying anyway, but it would be waiting on you. Now, granted, you'd have a lot more fractions and stuff there, but it just becomes really easy. Now, with all that, and we're going to be doing a lot of this moving forward, but with all that said, if you have a dependent situation, and there's 2 kinds of situations. I start talking about this for you new guys in part 2 at the very beginning. So there's notes on this. But a dependent is just what it sounds like. It means whatever you do on your first choice, the second choice depends on that. You saw that here, right? When I pick a red ball, my next probability is affected by that. It depends on what happens on the choice before it. When you have dependent situations, you don't have to do all these individual choices. You can do probability using combinations and counting the number of ways to be successful over the ways to just be successful or unsuccessful. And that's where you start getting down here into the using C's. So like right here, if I want the probability of 3 red balls, I don't have to do each individual probability and count the number of ways it can happen. I can just say, how many ways to get a red ball? Well, how many red balls are there? 5. How many do you want to choose? 3. So just like we defined yesterday, I'm going to choose 3 of those 5, and the order in which I chose them doesn't have an effect on the outcome. On the order in which I chose the red ones doesn't affect the outcome, so I use 5C3. How many total balls are there to choose from? 20. How many ways can you pick those balls? 3. 20C3. And if I were to write out 5C3 over 20C3, you know what I get? 5 over 20 times 4 over 19 times 3 over 18. And all the other junk would have canceled out. But if you didn't cancel it out, you'd also see a 3 factorial over a 3 factorial. Just like you saw earlier. Right here, how many ways can I get 2 reds and 1 white? Well, how many ways can I choose 2 reds if the order that those 2 reds were chosen doesn't affect the outcome? Well, 5C2. How many ways can I pick the 1 white? 6C1. How many ways can I pick 3 marbles from a total of 20? 20C3. And I know that that right there doesn't look anything like, at first glance, this right here, but it is the exact same thing. I'm going to show you that in a second. That is this. And in fact, this has that 3 factorial would have been right there, would have been in the bottom of that fraction, which makes it in the top when you divide by the reciprocal. This 2 and this 1 would have been on the bottom of the fractions in the numerator. That's that. These 2, 1, 3 make this part. So you don't have to worry when you use combinations, you don't have to worry about counting all the different ways the reds and whites could be rearranged. The combination has it built in for you. So you don't have to do this. This does all of that. Are y'all seeing that? Now, there are times when you can't use combinations. We saw it yesterday, flipping a coin, rolling a die. No matter how many times I flip that coin, my next probability is not affected by the outcome, is it? Seems like it should be, right? Like if I keep rolling that die and I'm like, every time I roll this dice, I get a 6. It starts to kind of mess with, or like every time I flip this coin, I've got 10 heads in a row. You start thinking either A, man, this thing only lands on heads, or B, I am due at tails. But that's faulty thinking if it truly is a good die or a good coin. Okay, so the point is, those are independent situations. With independent situations, the probability is not changing. The numbers are not declining like this. Well, 20, 19, 18 reeks of a factorial, doesn't it? 20, 19, 18. But 1/2, 1/2, 1/2 doesn't. I can't use combinations on independent situations like die, like coins, or even a situation like this. If I said, hey, every time you pick a marble, you have to replace it. If I replace it, then the numbers stay the same and my probability on my second choice is not changing. Those are independent situations. With independent, you cannot do combinations. You are forced to write out each individual option that you have and then count the number of ways it can be done. Now you're going to see that over and over, but the moment you lock into that and get that in your head, this is going to become more and more simple to you. Okay? And you got time. You do not want to shortchange this process. You want to do every problem on here and more if you can get a hold of them, and make sure you understand what's going on here. So like right here, a bag contains 5 red, 9 blue, and 6 white. Find the probability that if I pick 2, they're both blue. So using the fractions, what would you do? Well, what's the probability of getting your first blue? 9 out of what? 20. So you'd say, all right, the first blue, I'm just going to put a B there, would be 9 out of 20. This is doing one choice at a time. Now, once I pick that blue one, what's the probability of the next blue? 8 out of 19. Now, I have picked both blues. Now, then you have to say, how many different ways can I get blue, blue? Well, changing the order doesn't change anything, does it? Like B, 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 it's just one way. But if I was sticking to my rules, there are 2 letters, but they're both the same. And you can see that doesn't do anything. So in this case, not needed. Now, if I had used combinations, because I can, because this is a what kind of situation? Dependent. The second choice is affected by the first one. You saw that effect right there. I can use a combination and say there are 9 blues. I'm going to choose 2 of them. There are 20 total marbles. I'm going to choose 2 of them. That is the same as this. All right. And when they get uglier, I'll prove it to you and show you how it breaks down. Now, what if I got 1 red and 2 white? Well, I'm saying pick a red, then a white, then a white. So first, I'm going to do it with fractions. What's the probability of getting a red on my first choice? 5 out of 20. What's the probability of getting a white? 6 out of the remaining 19. Then what? 5 out of the remaining 18. So this is red, white, white. But I didn't say you had to do a red and then a white and then a white in that order. So what do I have to do? I have to count the different ways that I could arrange the reds and the whites and the whites. Because the probability of, look at the probability of going white, this would be white, white, red. Watch. White, 6 out of 20. The next white, 5 out of 19. The red one, 5 out of 18. It may look like it's different because the numbers are over different letters, but look, you still have 5, 6, 5 on the top, 20, 19, 18 on the bottom. It's the same. But rather than do this probability for every single option, I just go, why don't I just count the options? So I have 3 letters, 3 factorial. but 2 of them are white, 1 of them is red. And that counts the ways I could have done it. But if I see that it's dependent, I can use combinations. I could say I'm picking 1 red from what? From the 5 reds. I'm picking 2 whites from the what? 6 whites. This is counting the number of ways I could get a red and a white. And that does the math for you. And the definition of probability says the probability of the the number of ways to be successful, I just did that, over the total number of ways to pick 3 marbles, which would be 20C3. And even though it doesn't look like it, that is that. And I'm going to prove it to you. So here we go. 5C1 is really what if you were to write out that fraction right there? 5 factorial over 5 minus 1, which is 4 factorial over 1 factorial. 6C2 is what? 6 factorial over 4 factorial, 2 factorial. And then in the bottom, you get 20 factorial over 17 factorial, 3 factorial. Now, how do you divide by a fraction? You multiply by a reciprocal. So I am going to now show you why this is the same as that. Now, first, what happens when you cancel? What does a 5 factorial and a 4 factorial leave you with? Just a 5. There is your 5. What does a 6 factorial and a 4 factorial leave you with? A 6 and a 5, right? There's your 6 and there's your 5. What does a 17 factorial and a 20 factorial leave you with? A 20, a 19, and 18, but in the denominator, there's your 20 and your 19 and your 18. What's left? A 3 factorial on the top and a 1 factorial and a 2 factorial on the bottom. It's the same thing. You have 2 ways that you can write it. Now, I have some people that, and I think it was, I don't know if it was this period yesterday morning or afternoon, but they went, well, so you're saying that I can't use combinations with independent situations, true, but I could do this with both? And they're like, well, I'm just going to stick with this. Well, that's okay, except for one thing. What if I said there are 500 red, 900 blue, and 600 white, and then I say, what's the probability of getting 100 red and 200 white if I pick 300 marbles? Now, what do you find yourself doing? Writing out 300 fractions. Well, have fun with that. And yes, I do give you that question on the test because I want to see if the people that only use fractions can actually think in terms of combinations. So be careful. Yes, I can use this thinking, whether it's dependent or independent, all the time. Now, last thing, although we're not going to get into it right here, what would you do if I said, I want you to pick 1 red and 2 white in that order? If I specify in that order that I'm saying, hey, I want red, white, white, that's it. What do you leave off here? This, because that was counting the number of ways to do all the orders. I don't need that thing. So if you ever see in that order, just do your little fractions, but don't do this part. What do you do if you were using combinations? And I said in that order, or basically the order in which something happens has an effect on the outcome. Change it to P's. And when I change this to a P, what does it leave off here? If these are P, all P's, it leaves off that 1, that 2, and that 3 right here, which ended up being here. And if I leave off that 1, that 2, and that 3, that's leaving this stuff off. So if you ever see in that order, just use P's or get rid of this stuff. Last one on this little page right here. 1 red, 2 blue, 3 white if 6 are picked. All right, so using fractions. What's the probability? I'm going to do these in order. I'm doing a red, a blue, white, white, white. So red. What's the probability that I get my first red? 5 and 20. What's the probability that I get the first blue? 9 and 19. And then the next blue, 8 and 18. And then the first white, 6 and 17, because I keep getting less and less total marbles, right? And then 5 and 16, 4 and 15. Now, if I had said, what's the probability of getting a red and then 2 consecutive blues and then 3 whites in that order, I'm done. Because that is in that order. But if I don't say in that order, there's lots of ways to rearrange those letters and make new words, right? How many ways? You really going to count all those out? This guy's not. So what am I doing? I'm saying, well, there's 6 factorial ways, which is a buttload of ways, but just switching the 2 B's isn't going to make it look different, or rearranging the W's isn't going to make any difference. So just like with Mississippi, I divide it by 1 factorial for the R, 2 factorial for the B's, 3 factorial for the W's. And it doesn't matter the order. And yes, you can leave off the 1 because 1 factorial is still. Now, an easier way, I think, is to use combinations, right? So combinations would be 1 red. So I'm picking from the 5. So 5C1, 2 blues from the 9. So 9C2, 3 whites from the whites. So 6C3, and I'm picking 6 marbles from the total of the 20, 20C6. But these are equal and totally acceptable. And what would happen if I said, if get this in that order, what would you do? Make these P's, because that won't count. It won't get that 1 factorial, 2 factorial, 3 factorial, 6 factorial that end up here. And here, if I said in that order, I would just do this, but that is that order. So I don't need to count all those other ways that increase the likelihood of me being right. You seeing this? I'm telling you, you get this and you are easily on your way to a B. And then if you learn the other random stuff with junk and whatever, then you're on your way to an A. How about this? 14 students are in a class. 5 of them have blue eyes. If 4 students are chosen at random, find the probability that this occurs. All have blue. So with fractions, right? If I'm picking 4 students, right? 4 are chosen. So the first guy has a blue right here. Blue. So I'm going blue, 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 blue. So first is a blue, which said 5 of them have blue. So what's the probability that my first choice is blue? 5 out of the 14. But then once I pick that, the next choice, 4 out of 13, 3 out of 12, 2 out of 11. And how many ways can I do this? Just 1. But if you really wanted to be legalistic, 4 choices, 4 factorial, but all 4 of them are the same. You probably won't see that on my keys, but that would all cancel. So this is fine, or the whole thing is fine either way. And if you use combinations, what would you say? There are 5 blue-eyed students, but I am choosing how many of them? 4. There are 14 total students. I'm choosing what? 4. That and that are the same. Are you with me? And if I said in that order, actually, you'd be still right. Because this 4 factorial on the bottom and that 4 factorial on the bottom would end up canceling. So essentially, this and this, when there's only one thing being chosen, switching that to a P and canceling and not writing this stuff doesn't do anything different. You should put a P because it sounds like you should, but it would have still been right. I would have had to give you credit. All right, what about this? 3 have blue eyes. Now, if I say 3 have blue eyes, does that mean I only picked 3? No, I said that I picked 4. So that means one of them, 1 doesn't have blue. Okay, so you have to think about that. Even if I just specify what does work, you have to assume that the rest doesn't. And sometimes I'm very particular about that. But all right, so 3 have blue. So this is basically saying blue, 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 not blue. Okay, so help me out with that. Anybody? With fractions. Blue. 5 out of 14. Next blue. Next blue. So it starts out looking just like we did. but the final not blue. Well, if 5 have blue, then 9 must not, right? So the last not blue, there's a 9 in 11 chance. But this would be in that order. What do? How many ways can I rearrange those? And you can put a 4 because it's very countable. I could have n in either of those 4 places. Or you could say 4 factorial, 3 blues, 1 not blue. But if I were to use combinations, what could I say? There are 5 blue-eyed people. I am choosing 3 of them. There are 9 non-blue-eyed people. I am choosing 1 of them. There are 14 total people. I am choosing 4 of them. And what happens if I say in that order? These become P's, and that gets eliminated. Now, at least 1 has blue eyes. So what does that mean? At least 1. That means I could have what? That means I could have 1 blue-eyed person and 3 non-blue eyes, or 2 blue-eyed people, right? And 2 non-blue-eyed, or 3 blue-eyed people and 1 not blue, or what? All blue. Now that's 4 separate problems that each look like this. That sounds terrible. Terrible. I want to get that. Somebody. He says terrible. Notice? No. I don't watch like TNT, Charles Barkley. Terrible. You always say, it's terrible. Go watch it. It's fun. Just he'll say it at least once in a while. It's terrible. Terrible. He's a Birmingham area legend. Went to Auburn. Grew up in Leeds.
Anastasia met him in like a bar once.
Yeah, he's awesome.
No, it's the story she told us that she met.
Yeah, he'll take pictures with you, sign autographs, have fun with you. Like, he is a true gem. He and Shaquille O'Neal are 2 gems of America. I mean, they're fantastic. Shaquille O'Neal literally does this in his free time. He'll just go to ring stores or Walmarts and hang around. I don't know if you know this. He'll hang around the layaway department, or he'll see some guy that looks like he's struggling, walk up with a ring and try to start paying for it. He just swipes his card. He like buys them. Like he'll go during Christmas, he'll walk around Walmarts and see people going up to the layaway counter to kind of put stuff away. And he goes, I got this. Dude's awesome. He's like, man, $2,000. I thought it's nothing to me. Just pay it forward. True gem of America. Anyway, but guys, this sounds terrible. But what did we say about the complement? Very first day, we said sometimes it's easier to find the probability. Remember we talked about like the probability of rain is 20, then the probability of not rain is 80. So what did I do to get that? I went 100 minus that 20 to get the 80. Well, probability deals in 1. So if the probability is like 1/10 that it rains, what's the probability that doesn't rain? 1 minus a 10th, 9/10. Well, to find the probability, if I have to do all of this to find the probability of success, right? Wouldn't it be easier to just go 1 minus the probability that I don't succeed here to get success? Does that make sense? So what's the opposite, or what is not? We call it the complement. What is not at least 1 has blue eyes? No blue eyes, or all non-blue, right? So why don't I just find the probability of all non-blue and subtract it from 1? So the probability that at least, I'm going to just call the probability of success, at least 1 has blue eyes, is 1 minus the probability that none have blue eyes. So how do you do no blue? Well, 9 don't have blue, right? So you could say 9 over 14, 8 over 13, 7 over 12, 6 over 11. That works. And since it's non, I could do 4 factorial over the 4 factorial, but it's not needed. I could also say there are 9 non-blue-eyed people, and I want all 4 of them picked from that group out of a total of 14 people, picking 4. I could do that. But it makes it a whole lot easier than doing each and every one of these. Now, I give a test problem every year where it's like at least 1 has whatever, but there's like 10 blue-eyed people instead of just 4. So to do individually and then add them together, remember ORs mean add each of these probabilities together. There's always some poor sap who literally writes out all 10 of them instead of just going 1 minus the one that doesn't. And sometimes there might be 2 that don't, right? But that's a whole lot better than 10 that do. So think about that. This is called using the complement. And anyway, whole lot easier to do that sometimes than it is to do this. All right, so probability part 2, you're going to start seeing a lot of this that we've already been talking about right here. In fact, the first thing I was talking about here is about counting the number of ways that experiment or that event could occur. That's what that little fraction out in the front is. And I'm showing this example. Actually, this is an independent situation, sort of. Now, if you ever play baseball or softball, you know that every time you get up to hit, barring a sacrifice or whatever, it affects your batting average. You get a hit, your batting average goes up a little bit. You strike out or ground out, your batting average goes down a little bit. So technically, that is a dependent situation. Technically. But if I told you that Tarzan had a batting average of 300, you really don't know. Well, has he only batted 10 times and got 3 hits? Has he batted 1,000 times and got 300 hits? I don't know that, right? I just know a decimal, just an average. So if I know that, that's saying, well, all I can really deduce from Chipper Jones had like a 300 lifetime. He's a Hall of Famer. He used to play for the Braves. But he has I think in the last month he was in the league at age 38, his batting average dropped to 299. I was so sad. I was like, dude, quit now while you're ahead. He had a 300 lifetime batting average, especially. I mean, that's amazing to be able to do that over the course of your life. But if he gets an extra hit, I don't know the numbers about Tarzan to know how it's going to change. So I have to assume that he's a 0.3 hit, 0.7 not hit, and I have to treat it independently. So if it's an independent situation, right, and I don't know enough to be able to know how it's changing, then I can't use combinations. So I am forced to do the fractions, the individual at bats. So if the question was, what's the probability that he gets 3 hits in his next 5 times at bat? That would be 3 hits and 2 non-hits, right? All right. And we'll take, if you really know baseball, we'll take all the sacrifice bunts or whatever that don't count against your average. We'll take all that out. Okay. So bottom line, we're saying hit, not hit, not hit. So we've got 3 hits in here, 2 not hits, but this is definitely, didn't specify it in that order, did it? So 3 tenths, 3 tenths, 3 tenths, not hit, 7 tenths, 7 tenths. Now that would be wrong because if I stopped right here, this would be calculating what's the probability that he would get 3 hits in his next 3 at bats and then out the last 2 in that order. So if it said in that order, I don't need that. But if it does, I need to either count up the number of ways, which would be terrible, or say, well, there's 5 letters or 5 things to arrange, 3 of one, 2 of another. And when you simplify that, you get 10. And it counts those for you and keeps me from having to do that suffering. Are you with me? So that's how I want you to think. But just so you know, and we're not going to do the math on all this shit, just so you know, and I don't have to write it like this, by the way. Also, when it's independent, the probability is not changing. So don't write 3 tenths, 3 tenths, 3 tenths and waste your time. Just go ahead, 3 tenths cubed, 7 tenths squared, and plus the 3 and the 2, and they end up being down here unless it's said in that order. But you have to do the fraction thing. I can't do combinations with this. I mean, think about what would I even do? I mean, how many? I don't even know what to pick from. It's not like I have a tangible number of things, right? It's like it's this mythical number out here, 3 tenths, 7 tenths, whatever. So anyway, we can look at this. Here's another situation. But I'm talking about independent and dependent. We already defined that. There's your definition if you want to go back and read that. And then I just kind of want to start doing some of these. So the first question says, identify them as independent or dependent, and then see if you can calculate the probability. So 2 cups of coffee, 4 cups of tea. Dave drinks 2 of the cups. What's the probability that the 2 he drinks are coffee? So what's the probability that he picks 2 cups of coffee from these 6 cups that are on the counter? Now, does that sound dependent or independent? It sounds dependent to me, because if I were to grab a cup of coffee randomly, right, if I just saw the cups and I didn't know what was in them and I grabbed one, regardless of what I pick, there's now less coffee or less tea and less total. That sounds very dependent, right? Now, if he drank it, spit it back into the cup and put it back, then I guess maybe you could argue independent because there's now the same cup, although one of them is slightly tainted. But if that was the case, if there was something like I'm putting it back or it's dice or something like that, then independent. But in this case, I have two options, fractions or combinations, because it is dependent right here. So this is definitely dependent. Oh, and by the way, there may be situations that could be both. Like, how about this? All right, there's what? 1, 2, 3, 4, 5, 6. There's 10 of you. We're going to play softball, and I need a batting order, so everybody get in line. Now, if we're just having fun, right? Playing softball, and we're just whatever, does it really matter? I mean, it does, because you're going to keep scoring, you play to win, right? But, I mean, but if I just said go back, go up there and kick or whatever, you could all get in there. So if I'm looking at that and I'm going, hey, the order in which it's done doesn't have an effect on the outcome, whatever. And I might say a situation like that was a permutation. Sometimes it's a combination. Like if I said technically, like I think the batting order has a huge difference in the outcome. Right? I want to put my fastest guy, maybe the fastest guy who gets the most walks, gets the highest base percentage. May not hit for power, but he's on first. He's ready to maybe steal. Guy that can get me a run early. That's what I want hitting, leading off. I want a guy that can just crush it, like Luke, if you played in our softball game, or you guys that were just like beasts out there on the kickball field. I would want those like in the 3, 4, 5 hole, like to clean up the bases and get as many people in. Those things are important, and the outcome might make a difference. That would maybe affect whether it's a permutation or a combination, whether the order matters or whether it doesn't. And sometimes you might see situations like that with dependent or independent, but usually dependent, independent is pretty clear. Sometimes permutation and combination is not. But here I'm definitely dependent. And if it's dependent, I can use fractions, choice by choice probabilities, or use the definition of probability, count the number of ways with combinations. So right here, talk to me, 2 cups of coffee. What's the probability that they're both coffee? So coffee, coffee. First cup would be what? Probability? 2 in 6. Once I drink that, second cup, 1 in 5. Now, rearranging that order is not going to do anything. 2 letters, both the same. So if you left that off in this case, you'd be fine. All right? Which means the answer to this, even if I said in that order, you'd still be fine. All right? Now, with combinations, I could say there are 2 cups. I'm choosing what? Both. And there are 6 total cups, of which I'm choosing 2. This right here gives me the same outcome as that right there. All right, what about in a bag are 5 oranges and 4 tangerines? Biff selects one, replaces it, selects another. What's the probability that both selections are oranges? Because I put it back, we call that with replacement. This now becomes a what? An independent situation. So if it's independent, what can I not use? I cannot use P's, C's. I can't do it because those are factorial in nature and nothing's changing, right? It's still going to be 5 orange, 5 orange, 5 orange, 4 tangerine, 4 tangerine, no matter how many picks if I keep putting them back, right? So what's the probability that both are oranges? Well, if I was using fractions, which I have to in this case, what? First probability is what? 5/9 that I get an orange, and then that I get the next orange would also be what? 5/9, which means I can write 5/9 squared if I want. Now, I still have to count the orders, right? So 2 oranges, 2 factorial, up, they're both the same. So if you didn't do that, in this case, it would be fine. A green and a red die are thrown. Now, be careful about green and red die. If it says 2 die are thrown, think about it. Make sure you lock into this. If I say, and don't specify color, and I said, what's the probability that I get a 4 and a 5? Well, if they're both white, I could get what? Like if just say they were both white dice, I could get a 4. What are we saying? A 4 and a 5? Or a 5, couldn't I? But couldn't I also take this die and flip it over and get a 5? And flip this one over and get a 4 on it? So there's really 2 ways that outcome could occur, couldn't it? But if I say, hey, I've got a red die and I've got a green die, what's the probability that I get a 4 on the green and a 5 on the red? I can't go a green 5, 4 red. That's not an option, is it? So when you start seeing different colored dye in there, being specific, it's almost like it's saying, hey, the order has an effect on the outcome. Don't think this way. So what's the probability of getting a 4 on the green die? 1 out of 6. What's the probability of getting a 5 on the red die? 1 out of 6. So getting a green and a red isn't any different than getting a red and a green in this case, because it's still the same thing. So when you start seeing that, it's kind of an illusion a little bit, but it's kind of like saying, hey, in that order. If I just said, eliminate this, and I said 2 die, 2 are thrown, what's the probability that I get a 4 and a 5? If I said that, then you wouldn't have this. And I could say, wait a minute, I got a 4 or a 5, or I could also get a 5 or a 4. I would have to go back and say, well, there's 2 dice, but they're and 1 of each. 1 4, 1 5, 1 5, 1 4. I would have to count the number of ways. Or you could say, on my first roll, there are 2 options that would work, right? I could get a 4 or 5 out of the 6, but once I get that 4 or 5 on the next roll, I got to get the one that I didn't get. You could also think like that. Still gives you the same outcome, doesn't it? But that's neither here nor there, because on this particular example, I did say green and red, so none of that other stuff matters. It's just 1 6 1 6. What about this? Barbie plays Ken and backgammon. The odds are 4 to 3 that Barbie will win. Well, I just snuck odds in there, didn't I? Odds doesn't work well when I start doing all this combinations and permutations. So my suggestion yesterday, it continues today. Always change your odds to probability and work with that. And in the end, if it happens to ask for odds, convert it back. But we live in probability. That's where all of my rules make sense. So right here, if the odds are 4 to 3 that Barbie wins, we're going to say the probability that Barbie wins is what? 4 wins, 3 losses, right? So that would be 4 what? 4 7ths. The probability that she wins is 4:3. The 4 is the wins, the 3 is the losses, add them up. So that's the probability that Barbie wins. Now, what's the probability that Ken wins? Well, if she wins 4 7ths of the time, what does Ken win? 3 7ths? Well, you'd have to assume that, I guess, right? Because you don't really tie in backgammon. All right, so the question is, what's the probability that Ken will win the next 4 games? So Ken's winning 4. So I'm going Ken. Oh, that's unfortunate. Ken, right? All right, so I've got Ken winning 4 times, so 3 7ths. But is this independent or dependent? Independent, right? Because the probability of Ken winning isn't changing. Now, in real life, if Ken kept winning, you'd probably go, if you were keeping a record of those wins, you'd go, wait a minute, Ken's won. You keep saying the probability is 3 7ths, but he's won freaking 10 times in a row now. I think the probabilities have changed. So like batting, if I knew how to calculate that, great. But if this is all I know, I have to use it. I do this. That is just bothering me. Ken wins, yada, yada, yada. Okay, now, technically, I have to say, well, there's 4 of those, 4 factorial. Oh, but they're all the same. So, not technically. I mean, if I'm really sticking to my guns right here, I would say something like that. But if I accidentally forgot, or if I just chose not to do it in this case, whenever these are all the same, I don't have to do that because it's just one way of happening. One. All right, got a few more minutes. In a bag are 4 red, 4 green, and 7 blue. 3 are taken. What's the probability of selecting a red, a green, and a blue in that order? Dependent or independent? Dependent, because every time I pick a marble, there's less marbles. But in that order means I don't have to do what? I don't have to do that stuff out front, those factorials out front. I don't have to do it because I don't have to count the different ways. It only is going to occur that way. And that means I would use what if I was using the C's and P's? P's. So one way of doing it, and again, this is red, green, blue, red, green, blue. I could say probability of getting a red is 4 out of 15. But then the probability of getting a green is 4 out of 14. And then the probability of getting a blue is 7 out of 13. But because it said in that order, I'm not going to count the other orders. I'm done. But if I wanted to use the other option, I just don't use C's. I go, there's 4 reds. I'm going to pick one in that order. There's 4 greens. I'm going to pick one. There's 7 blues. I'm going to pick one. That's the number of ways I can get a red, a green, and a blue. But what's the total number of ways to pick 3 marbles from 15? If the order doesn't matter, 15P3. And if I didn't mention this yesterday, P's, this is like saying the first number in 4 factorial, 4. The first number in 4 factorial, 4. The first number in 7 factorial, 7. The first 3 numbers in 15 factorial, 15, 14, 13. So that's another one. That's how P's work. All right, bell's about to ring. Anyway, this is, see what you can do on the rest of these guys. Really do, especially if you didn't have a good dose of this last year or you struggled with this. And come talk to me if you have issues after school or before school. And let's get you in a good place.